All right. Good morning. This is Mr. Felton, and we're on a bright Monday. It's a little bit cold again for early May, May 4th. And today we're in the chapter 15. This is our first section in chapter 15. And I'm going to give you a good 8 minute to 10-minute video on that first section leading up to the first problem. So this is something that's worthy of an explanation in a video because it gets a little bit tough for you to read. And the ideas today are down the list, and what we're trying to get accomplished is what is energy? How does it pertain to potential and kinetic? Things you've probably talked about in seventh and in maybe even ninth grade. How can this potential energy be related to heat lost or gained? And how is the amount of heat absorbed or released by a substance calculated as its temperature changes? And with that, we're going to talk about a law and a couple of conversions. Things that you may need to know along the way. Temperature measured in Celsius as we get further into chemistry. It's Kelvin. We've already talked about Kelvin. We do a couple of conversions into Fahrenheit here and there because that's what we measure here in the United States. And then all of the definitions on the side that we have to get used to be able to understand our problems today. Energy, the ability to do work. So in ninth grade, we talk about this and we do some problems with this, but it exists in two forms. Energy at rest, which is potential, and kinetic or moving energy. And that is all important in the different things that we talk about. Potential energy, all measured in joules, and that's important as well. And kinetic energy is energy in motion. So, very important, and kind of a question that you eventually get to is the law of conservation of energy. And within a closed system, energy is neither created nor destroyed. It can be converted into lots of different forms, but it can neither be created or destroyed. And that's our big thing today if you're looking at it in different ways. So we're talking about energy neither being created or destroyed. Within this, we measure energy, and energy is measured in joules, and the general conversion is a joule is equal to so many calories, and calories to kilocalories, and joules to kilojoules. And you need to be able to understand these little things because there are some problems that you're going to deal with that simply have you convert the two and go back and forth with that. First problem that you're going to deal with, and this is your first set of problems, 1, 2, and 3, is simple conversions. And this is no different from what we've talked about before in conversion. You have your problem. You put that problem. I usually take that and put it over 1, and then you throw your different units in. So we have calories to joules. So this would be over 1. There's 4.184 joules in a calorie, and we do our conversions to get to joules. So this is no different from anything we've done before. It's just new units. So within this, analyze your problem, set it up. I usually put this over 1 or box it as we go across, but this is the fractional dimensional analysis that we usually do in school. And that's going to take you through question 1 and 2. And those questions 1 and 2 and 3 are on page 519. Okay, let's talk about the next phase of this once we do problems. So sig figs are important because of our first question. Being within 2 sig figs, 230, so our answer has to be in 230. But you're taking us through dimensional analysis and fractional crossing things out. Now, important in this unit, and this doesn't go away when we talk about calculating energies, is something called specific heat. And it reads as any substance, specific heat of any substance is the heat required to raise 1 gram of a substance. So if you have an amount, 1 degree Celsius. So it's the energy. So joules of energy, 1 gram of a substance, 1 degree Celsius. So if you look, water, it takes, quite amount of energy. Going down the list, there's a lot of different things um, that have calculated specific heats that we use, and we'll use these in problems. This will be your next set of problems, dealing with how to do this. And to be able to calculate a specific heat, we've got an awesome formula, with Q representing the heat absorbed or released, and that's a positive or negative number. We're going to get used to that. C represents the specific heat from this chart, so that's where your C comes from. You'll gather it from there. Your change in temperature is got to take place, because remember, specific heat and calculating this involves a temperature change. So you subtract two temperatures and then your mass in grams. So this is your formula. And of course, algebraically, we in chemistry try to mesh up. So you'll solve for C, you'll solve for M, or your change in T. So, problem within this. In the construction of bridges and skyscrapers, gaps must be filled between adjoining steel beams to allow for expansion and contraction of the metal. The temperature of the sample of iron with a mass of 10 grams changed from this to this releases so many joules. What is the specific heat? Now, you could look back and see the specific heat, but they want you to actually calculate what was in that chart. So if you go back here and look at iron, well, iron's specific heat should be that, but we're not. We're actually calculating, seeing how close we can get to that. So within that, we have a problem. We've got a change of temperature. We're calculating for Q. So we've got our C, our M, and our change of T. So when we put this all in, we analyze the problems and figure this out. So energy released, and I'm going to move my thing here. You've got your mass of iron, you've got your temperature change, and you've got your energy released. So the specific heat of iron is calculated for C. So C itself is Q over M times your change of temperature. So we take that, put those in, and if you look, all of the units stay, because we don't cross anything out, and we get exactly what is in that chart of 0.449 joules per gram per Celsius. And the algebra behind this, can be changed depending on what you're solving for, or you can simply solve for X. So our answer is reasonable, because it's exactly what is in the chart on table 2. Cool. So good luck. Your questions from this are 1, 2, 3 on page 519 and on 521. The exact kind of same problems from this 4, 5, and 6. Good luck. Have fun. Enjoy your Monday.